So this is your quandary. Guys, can we be quiet? Hello? So step 1, 112 nanometer light strikes a metal. We know the work function is 4.41, so that's the energy needed to take electrons off. Okay. What's the first thing we do with 112 nanometers? Make it into what? Yeah, well, it'll be after that. Calculate the energy in joules or electron volts. Always electron volts. Always solve photoelectric problems in electron volts, right? So 112 nanometers. To turn it into electron volts, right? To turn it into electron volts, it goes something like this. What I'm going to do is I'm going to go hc over lambda, right, is our energy. Not in the data packet, by the way, right? Okay, so that's 6.626 e minus 34 times 3e8, right, divided by 112 e minus 9.
Okay, so it has to be meters when you're multiplying it, and it also has to be EV when you're multiplying it?
I'm going to get joules here, and I'll show you when I turn it into electron volts. Hold on for that. Hold on to that thought. Okay. So let's see if I've got this. I do. Whoops. Guys, can we stop? Thanks. Okay, I'm getting that this is 1.7748 times 10 to the minus 18th joules. Yeah? Not done yet, though, but I don't know why I circled it. You know? Okay, and then how do we turn that into electron volts? Divide by... Right. In fact, Andrew Shin last period was he just made a formula. He just said, look, it's always divided by E, right? You know, he made it. Yeah, I know. It's like, where'd you get that? Yeah, there it is, right? Okay, so I'm going to divide by 1.602 E minus 19. And there we go. And really, I mean, God help you if this is anything other than just like, I hit your knee and your knee just goes out like that. I mean, if you're thinking about how to do this, this is the basic thing that we have to be able to do. You have to be facile. You have to be able to go from electron volts to this to electron volts. And if you can't, go study that, okay? Because honestly, God, this is not going to make sense if you're thinking about this, right? Okay, so this is 11.07878 electron volts, right? And now we set this up. This is the photon energy, correct? Right? So where does that energy go? Well, that energy goes to work function 4.41. Gee, how much is left for kinetic energy? So I'm going to subtract 4.41, and it's 6.666. It's 6.6687. Yes, isn't it? Yeah. Yeah. Okay. So it's 6.66878. I think this was in my phase where I was making numbers come out evenly to 666 or something like that. Okay. There was artists have these phases, right? This is that's my phase. I think of myself as kind of an artist. Now, there are two ways to say this, and they are the same thing. The question says, what is the stopping potential of the ejected electrons? Well, they have an energy of 6.66 blah, 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 right? Electron volts. What is their stopping potential? 6.66878 volts. They have a kinetic energy of 6.66878 electron volts, and they are stopped when they fly through a potential of that many volts. It's the same thing because we're talking about an electron. If you ever talk about something that's not an electron, that has a different charge, like an alpha particle, be more careful, but there we go. Are we good? Yeah. Okay, so you can talk about it either way, and there we go. Yeah. Yeah. 112. We used it right there. Yeah? Yeah? I know, or just, yeah.
Why is it called stopping?
Because the electrons fly off of the photocathode or whatever it is, right? And they're flying through space, and you've got to, actually, so they're decelerating. So the voltage is decelerating, it's stopping them. It is the potential that stops them. Yes?
Okay.
Yeah? Yeah. That's cool. Did you stamp it? You haven't. Yeah, go for it.